Okay, so this should work. So thank you so much for having me. I'm now going to talk a bit about our efforts in maintaining a library for mathematics, a library that I think all of you, or most of you, have heard about yesterday in Kevin's talk. I'm talking about mathlib. So mathlib is a mathematical library for the lean proof assistant. Yeah. And even more, it is the library. It is the de facto standard library for lean. Lean and mathlib are based on dependent type theory, a variant of the calculus of inductive constructions, and we heavily use classical logic and the axiom of choice. And there is a huge and active community around mathlib, which is centered around GitHub, where all of the code contribution happens, and for Zulip chat for discussions. Nope. So what is in MATLAB? There is a lot, mostly I'd say like undergraduate mathematics. This is an excerpt from our overview page on our website. And this is just like the last page of it. You see there is something about computability theory, set theory, inner models of CFC, analysis, topology. I mean, it goes on to algebra, field theory. There is a lot in MATLAB, and it is growing quickly. So when MATLAB started in 2017, it was forked from the Lean standard library. And at that point, it was around 30,000 lines of code. Now, 3 years later, we are at 300,000 lines of code. And the rate of growth is only increasing. If we look at the commits we have per month, these are skyrocketing. At the moment, we have around 300 commits per day. And 300 commits per day, that is around 300 commits per month is about 10 commits per day. This is 10 pull requests per day. And these are made by a large variety of contributors. So that just in the preceding 30 days, we've had around 44 active contributors on MATLAB. That is 44 people who got pull requests accepted into MATLAB. And these contributors, their background varies. I mean, they range, as we've heard yesterday, from undergraduates to tenured professors, from mathematicians to other professions. And many of those contributors are research mathematicians and not primarily interested in software engineering and maintaining these large systems. So the procedure for getting contributions accepted into MATLAB is that there is a group of about 15 maintainers who can merge pull requests on MATLAB, and we also try to review them and give comments and request changes on those pull requests. Also, people aside from the maintainers do this reviewing process. Nevertheless, there is a lot of pull requests to review. There's a lot of contributions, a lot of change, and hence we've been looking into ways to make this contribution workflow easier, to simplify the reviewing process, and just increase the general standard of code in MATLAB. Now that it's so much, you need some better infrastructure to have an overview of MATLAB. You need some documentation, and it would be nice if the library would look mostly the same in various places. So we've done several things to make that happen. So we've launched a documentation website where documentation from all declarations in MATLAB and also tactic documentation and various design decisions are visible on a nice interface where you can click through it. We also have some nice integration with Zulip where you can just write short links that are automatically hyperlinked to our documentation. And then the main contribution of this talk is a set of linters that we have, so a set of tools that automatically check the code for common problems. And these are run during continuous integration. So whenever you make a pull request to MATLAB, so we have a setup using GitHub Actions, where on every commit, MATLAB gets built. And then once MATLAB is built, these linters are run and the documentation is generated. And if there's anything wrong with MATLAB, you will get a red check mark, a red cross on your pull request, and we won't be able to merge it until you fix it. And in this way, we enforce a baseline quality standard in mathlib. Okay, so let me first tell you a bit about the linters, and then I'll tell you a bit more about the documentation. So linters are lean meta programs. In lean, meta programs such as tactics are implemented using the same syntax as definitions. They're just lean functions, albeit they are lean functions that use some built-in types and constants for the expressions and the environment and all the internal data structures of lean. So a linter here is then just a function in the tactic monad which takes a declaration and gives back either an error message or nothing, so an option of a string. And being in a tactic monad means that it can access all the same things that a tactic can access. It can infer the types of terms, it can look up declarations in the environments, it can invoke more complicated tactics like the simplifier. And so this is really a nice setup. And importantly, we do not check the source code. We do not look at if there is enough white space there, but we actually look at the elaborated declarations and try to find issues there. So as I've said previously, these linters are typically run as part of the continuous integration workflow when you submit a pull request on GitHub, but you can also run them locally before submitting the pull request. And in fact, this is good practice just so that you can quickly fix the errors without having to look at GitHub. And for this, you just write #lint in your file, and then a message will appear telling you what is wrong with what you wrote. So let me show you 2 example linters. We have got about 15 of them in total, so I'll just pick out 2 interesting ones that might also apply to other systems. So the first one is a very simple linter. It checks for unused arguments in a definition. So since lean is based on type theory, this actually checks for 2 interesting things. So first, it checks for unused arguments in definition, where you are, for example, where you write a function that does not depend on one of its arguments. The linter will detect this and flag it for you. And the other equivalent thing is it can also check for theorems, whether they do not use one of their assumptions, one of their hypotheses. And this can happen more easily than you might think. If you look at the example here, we have a small lemma. I don't know, this might occur somewhere really as a small lemma for the actual theorem that you want to prove, that if 2 times x plus y is less than 10 and 5 is less than y, then x is less than 5. And you really don't want to prove this by hand, so you invoke a nice tactic, and you never notice that, well, one of the assumptions wasn't even necessary. And in such cases, then the linter will actually tell you, oh, you did not use 5 less than y. Yeah. And then you can remove it, and you have a much nicer theorem. Now, this linter is not only very useful when you're writing code the first time. And when you write code the first time, it will help you write it correctly, but it can also help you if you change something else in mathlib. If you do some large-scale changes where you refactor one part of mathlib, and then you kind of want to adapt all the rest. And with linters, this becomes much easier because they will flag little inconsistencies that unexpectedly pop up. One example that happened recently was this theorem here, which says that 1 over a to the nth power is 1 over a to the nth power. And since division by 0 is a bit of a weird thing, we assumed that a is not equal 0. Now, in March this year, we refactored the theory of fields a bit and added a new axiom. Well, this time the axiom says that the inverse of 0 is well defined. This is a really useful assumption, and I think also other systems like Isabel and so on use this one. I can only recommend it, it's very useful, because many theorems such as this one now need one fewer hypothesis, and the linter will point this out for you. And in this way, these you do not introduce new subtle errors in code that you didn't even look at. Instead, the linter ensures this for you over the whole code base, where even in instances like this one, where no reviewer would have ever looked at it. And this is actually a commit from mathlib. So in the change, in the pull request where this happened, there's actually one commit which says remove unused arguments. So apparently somebody looked at the linter and fixed it. Now, it's not always the case that you want to fix every single problem that linter points out, because half of the point of this, having these as linters and not as fatal errors in the proof assistant, is that they are not always correct. So that then the linter does not always point out an issue. Sometimes you actually want to do what the linter tries to forbid. For example, sometimes you actually want to have arguments that you do not depend on, such as if you define the constant function. Then, of course, one of the arguments is not used. And in this case, you can write attribute nolint unused arguments above it, and then the linter will ignore it. A similar technique is used for definitions that were in mathlib before we introduced the linters. So we introduced the linters a few months ago, and at the time, of course, most of mathlib did not follow these standards. So we tried to fix a lot of them, but there are still a lot of these old errors in mathlib that we still continue to fix, where the linter would say they're wrong, but we can only fix them over time. So we have a file called nolint.txt, which contains the list of declarations, which were where the linter flagged it at the time of introduction, and these are exempt from our new linting requirements. In a sense, they are grandfathered in. Okay, so this was like, I promised you I will present you 2 linters. So we've now seen a very simple one, and now let me show you a bit of a more interesting one, which concerns the simplifier in Lean. So Lean, like other proof assistants such as Isabelle, has a simplification tactic. What does this tactic do? It does term rewriting using the lemmas, which you mark via the simp attribute. And this is really useful because you can do really cool stuff using it. For example, if you want to compute the complex derivative of the function cosine of sine of x times e to the x, then the simplifier can do this for you. You don't need to know how the lemmas are called. You don't need to chain them. You don't need to write a large tactic. You can just write by simp, and this is all done for you. And since this is so useful, a lot of lemmas are marked as simp in mathlib. So it's, at the time we wrote the paper, it was more than 7,000 lemmas. Now let's quickly recap how the simplifier works in detail. So as I said before, the lemmas that you want to rewrite with, you will add a simp attribute. So here at the top, we have 3 lemmas, very simple ones. The names are like they would be in mathlib. So we've got a lemma that simplifies 0 plus x to x plus 0 to x, and x times 1 to x. And then the simplifier will apply those in turn to rewrite, well, any term such as, for example, the one we have here. And it will do this in a innermost first way. It will start first with the arguments of the term, and then proceed recursively with the enclosing term and the enclosing term and so on. So in this example here, it first rewrites the innermost term, x times 1, and then once it has simplified x times 1, it continues with x plus 0, 0 plus x, and then it reaches x, where it can no longer rewrite anything. And then we say that x is in simp normal form. Now, one consequence of this algorithm is that it can happen very easily that some simplemmas may never be used. They become essentially completely useless. And this is when the left-hand side of the simplemma of the equation is not in simp normal form. For example, this lemma never used here will never be applied, because in any case where it could be applied, the simplifier would first simplify the right factor of the multiplication using the 0 add lemma, and then never used no longer applies. So this is maybe a really, really stupid and simple issue that is completely obvious when you look at it in such a small example. However, when you have a 350,000 line code base, it can happen very quickly that file A declares a simplemma, and that file B declares a simplemma on the other end of the library, and it turns out that this lemma in file B, well, makes the first one redundant. And these are very non-local effects that still happen very often, but are hard to spot. And hence, we've written a linter for this kind of scenario. So what happens if you write this never used lemma in mathlib? The linter will complain immediately, and it will tell you that, oh, this is a bad lemma, because the left-hand side simplifies to x times x. And it will also tell you how it simplifies, namely by using the zero-add lemma. So you have an idea about where to look to fix this issue, and it will even give you some advice on how to fix it. So in this case, it tells you change the left-hand side. In other scenarios, it will give you more targeted advice, such as telling you, oh, the other lemma might be a duplicate. And then you can decide which one of them to delete. So as I said, this very simple error occurs surprisingly often in practice. And even the first version of this linter, which still had some restrictions, found more than 100 redundant simplemmas. Most of the pull requests introducing this first linter consisted of actually fixing mathlib. And this is, again, typically not because these lemmas are defined in the same file next to each other and they make each other redundant, but quite often because there is a lemma in a completely different file, which simplifies things in a slightly different way. And maybe a more general point about these linters is that they make the system more accessible. They, like, if you just know about simp, then it's very hard to figure out whether you're actually doing the right thing. You can put the simp attribute on everything, and you don't know if you're doing things right. But if you get some feedback from the system that tells you, oh, you're doing something wrong here, then you suddenly get a bit more confident in using these tools. They become less of a black box, and you actually gain some understanding. And like I used to have really reported that this lintering outputs have helped them understand the system. So there's this quote by Kevin Buzzard, who's learned something about simp just by looking at the linter output. And in total, we have about 15 linters, and they do more than what I've just presented to you. So there are several classes of these linters. So some do purely statistic checks. For example, whether every definition has a documentation string. This is, I guess, a stylistic issue. Another one is that you use the right keyword to introduce a definition. So in Lean, you can use lemma and def almost interchangeably. So there are subtle differences, and that's why I want a difference between them. But you could conceivably use def for everything. But as a stylistic choice, we want people to use def for definitions that are not propositions, that are not theorems, and lemmas for definitions that are propositions, that in hence are theorems. So, and another class of linters concerns conventions we have in mathlib. So one convention is that we use the lesser equal relation in favor of the greater equal relation. Because the greater equal relation is just defined in terms of the lesser equal relation. So x greater equal y, if and only if y lesser equal x. And if we would use both relations, we would need at least twice the amount of lemmas. And so we try to standardize on the lesser equal relation. And there is a linter that tells you, do not use greater equals. Another such convention is that when you prove a theorem, you should freely assume classical logic. In particular, you should never use the decidable type class when proving a theorem, because you should use the axiom of choice instead. And hence, we have a linter that enforces this. So a third class of linters is like one that improves the performance of the system. So particular type class instances have particularly subtle performance issues. They can easily cause the type class resolution mechanism to loop, or it just becomes slow. And we've found out several issues there, several classes of instances that are prone to cause slowness in the type class resolution, and we've hence written linters that forbid them. You can still use nolint to, if you really are sure that you are doing this correctly, but most of the time these are wrong and you shouldn't use them. And if you look at the pull request made to mathlib, people will first write the wrong version, and then they see in the linting output, oh, I should change the priority of this instance. And then they actually do it. So this really helps make people write correct and idiomatic code for mathlib. So the full list is on our website. Okay, so let me at the end quickly come to the documentation we have in mathlib. So we have various kinds of documentation in mathlib. So if we can characterize them by how close they are to the thing that is being documented. So we have some kind of internal documentation which is directly next to the thing. So we have module docstrings, which are like long human readable descriptions of the content of a file, which comes at the beginning of a file. We have declaration docstrings, which are right next to a declaration and are supposed to describe what the definition is about. And then there are other documentation that is still in the lean source code, like still in the mathlib source code, but a bit further away from the corresponding definition. So these are one called library nodes. Those are to document design decisions. And the other one are tactic descriptions, which document multiple tactics at once. And then going even further away, we also have by now a lot of documentation on our website. And this is even more higher level information, such as style guides that tell you how you should name your lemmas and how many spaces of indentation you should use, and high level overview guides to parts of the library. Okay, so module docstring comes at the beginning of a file and looks about like this. It has a human readable description of the contents of the file and main definitions and maybe some key notations and implementation choices. And it is by now mandatory, although we don't have a linter for it. So declaration docstrings are docstrings that come right above a definition, and these are mandatory for definitions because otherwise the linter will tell you to write one. And there we render them on our documentation website in a nice way. So every name here is hyperlinked. You can click on it. You can also click to view the source code. And by default, we do not show the implicit arguments, but you can also expand them. And this documentation on the website, it really shows the view lean has of the declaration. It is generated from the elaborated declaration, not from the source code. So you really see the arguments, not as they appear in the source code, but how lean actually sees them. The library nodes, they're inspired by a technique from the Haskell GHC compiler. And as I said, they are used to document common design decisions in the code. So if you are formalizing cosets of groups, and you figure out that you should use the has-COE type class you shouldn't use the has-COE type class in a certain way, then you document it there, and then you run into this kind of stuff again. For example, the completion of uniform spaces, and there you just say, while we do this, C node use has-COE t, and in this way you can reference to the explanation you've had in the other file. These are rendered in a list on the website, and you can also click on them in the editor. And then finally, there are the tactic descriptions, which document a whole family of tactics. So most often for tactics, there are several variants of the tactic. For example, whether they work on the goal or whether they work on assumption. And like such a tactic description, they documents the whole family at once. And for each of these tactic descriptions, you get one entry in the documentation website. There's also a list of all of these tactics on the documentation website. Okay, so to conclude, I think people really like this kind of maintenance effort. So I think people are really happy about linters because they help people understand better about how the system works and maybe also make the contribution process a bit more easy. If like the pull request you make doesn't have very obvious issues where 5 people tell you, please put some documentation here. And also, like on the library, we've seen some noticeable improvements from this work. So the documentation has improved greatly after this effort, and also after introducing the linter. All new declarations have to have documentation, and hence the documentation grows. So also the simplemmas, they have grown better. We've fixed a lot of simplemmas so that they can actually work now. And maybe the most objectively noticeable improvement has been in typecast performance. All of these fixes we've piled up and that have been supported by linters that maintain these fixes and that make sure that people do not, that people actually do things in the way they should be done by using the right priorities and so on. The typecast performance has improved greatly over the last few months. And finally, the linters, I think, also have helped the reviewers quite a bit by taking care of the obvious and easy issues and telling our contributors to fix them before actually humans with limited amount of time need to look at it. Well, thank you very much.
Thank you. Thank you, Gabriel. Nice talk. Let's see if there are some questions.
Yes, can I ask a question, please?
Yes, go ahead.
Hi. So can you tell me, as a Dutchman, I mean, how do you feel about not having intuitionistic mathematics? If you're based on the, yeah, I mean, you know, intuitionistic mathematics is quite important as well. So how do you check intuitionistic mathematics when you have behind you the classical logic? Or
so
that's one question. I'll give you my 3 questions. Now, the language in which I have also looked at lean documentation, and I've seen the definitions and the proofs, it's really not what I see in a book of math. I really miss it's being able, it's wonderful to have it all implemented and checked, but I want it to be in the language of the book that I open. And, you know, it's hard to teach students. And again, I know, I'm sorry, I missed Kevin's talk, I was away. But in undergraduate education, I mean, how much do students like the math written in lean? Can we really change all of our math education to be doing it in lean instead of these beautiful math books? These are my questions.
I think there have been 2 questions. So question number 1 is, what do we do about intuitionistic logic? So the answer is, for mathematics, we use classical logic. I mean, if you use intuitionistic logic to formalize the real numbers, continuous functions, you get a completely different development. It would be something entirely different, and it's just not what we do. If you want to do intuitionistic logic in lean, you can do it as well. I mean, you can just ignore the axiom of choice. I mean, you can even embed homotopy type theory using some metaprogramming tricks into lean. But this has not really taken off in lean. So I guess we just focus on the classical parts, and there hasn't been any real interest in intuitionistic logic here. So to your second question about how does this look like math, and do undergraduates like it? So I don't really have any experience with undergraduates working in lean, but I think Kevin Bassett yesterday was very positive about their experience. He didn't really mention any big issues in undergraduates being able to understand lean. So of course, there are some technical issues, like in mathlib, we want to define things in a reasonably general way, which of course makes it harder to understand for people, for first-year students. But I mean, I don't think this is a problem of notation. Regarding notation, yeah, I agree. Sometimes the notation in lean is very much not what you would see in a book. For example, I mean, like intervals need to be different, summations need to be different. Yeah. Personally, I don't think that's the biggest issue. I mean,
you know, I think standing in front of the students and teaching them an undergraduate course in mathematics, you know, I know that it is hard for me to switch to teach them an undergraduate in lean because, you know, the tactics would be quite hard for me to introduce to them. And also, I want them to be able to do the proofs, to really be able to do proofs on pen and paper. You know, I mean, it's great to have the computer help, but I don't want them to forget this technique of being able to do proofs. That's one thing. Also, the other thing that I want to know is, There are courses that are difficult to teach the students for analysis, you know, when they reach doing limits and etc. Now, does using a pseudo-improver like lean make it easy for us to teach them this mathematics?
Maybe I can answer this question if you don't mind, Gabriel.
Yes, please. I think you have much more experience, Patrick.
So I'm Patrick Massot from Orsay. I'm a mathematician teaching mathematics to mathematics students without any computer science background. And for the last 2 years, I've been using Lean with first-year undergraduate students to do exactly that, learning how to write proofs about limits, analysis, real analysis, epsilon and delta as proof to first-year undergraduate students. And the goal of the course was not to teach Lean, it was to teach traditional pen and paper proof using Lean, and it just works great. And the students are really happy with this. And now I even have one of them is currently contributing to mathlib.
Fantastic. Do your colleagues also in the department
Sorry,
use Lean?
The discussion is very interesting, but I have to cut it short,
yeah.
as we have a long section. So I invite everybody to move it on Slack, please. So, Gabriele, remember to stop recording.
Oh, yes. Okay.
Moritz can share his screen.
It's a bit hard here. No, come on.